Hi, we are presenting depth from camera motion and object detection. My name is Amika Rahim, and this is my partner, Alan Floor. So just a little bit about the paper. In the areas of automated driving and robotics, accurately predicting the depth of detected objects is important for both obstacle avoidance and navigation. This is usually achieved through the use of interpreting raw data about the environment, which is gathered from 3D sensors. This paper introduces a method to estimate the depth of detected objects using uncalibrated RGB camera motion measurements in a sequence of bounding boxes. They create an RNN, which they name DBox, that estimates the depth using optical expansion and motion parallax. The authors also created the Object Depth via Motion in Detection, or ODMD benchmark, the first one of its kind, to train and test the efficacy of DBox. Here are some example depth results using a camera phone from the ODMD dataset. The authors identify a number of advantages to their approach. The use of RGB cameras for computer vision is not only common, but is also inexpensive compared to LiDAR or RGBD cameras, D standing for depth. The bounding box of a detected object only has 4 parameters, which makes their processing computationally inexpensive compared to RGB images or segmentation masks. Camera motion is already measured on most autonomous hardware platforms, so it's easier to get the measurements. Their method can also be used for other applications due to its flexibility in being able to use either bounding boxes, segmentation masks, or both. The DBox architecture was optimized for high performance on low GPU utilization, decreasing the necessary amount of computational resources. It's a modified long short-term memory, or LSTM RNN, with fully connected layers. To account for any possible errors in object detection, DBox makes sequential calculations for all n observations to estimate the final object depth. The authors use n equals 10 in this paper, and they performed a calculation of depth from a 2D image using the pinhole camera model. The ODMD benchmark consists of a series of bounding boxes, XYZ camera movement distances, and ground truth object depth. Some samples have been altered with added noise, including incorrect depth measurements and random movement for training purposes. The benchmark is made up of 21,600 artificially generated images for testing and validation. This allows DBox to learn how to predict the depth of detected objects with any combination of XYZ camera motion data. The DBox network was trained on ODMD in multiple different configurations. The configuration was trained on the benchmark with added noise has the lowest mean percent error overall for the ODMD benchmark, which is 4.5%, and did the best on the robot set at 11.2%. DBox ZP, which only considers z-axis motion, is the least accurate overall at 15.6% error, demonstrating the need for all X, Y, and Z motion inputs in training. However, this configuration performed the best overall on the ODMS benchmark, as well as for both the robot set and the driving set. DBox CP also only took about 4 minutes to train on bounding box-based inputs, while the runner-up, ODNLR, took almost 3 days to train on segmentation math. Here are some of the tables that were from the paper showing the results for the ODMD experiments and the ODMS experiments side by side. So some of the related work of this paper, the authors referenced their previous work, where they used segmentation masks in order to perform video object segmentation as the ODMS method. They also have previously used camera motion measurements gathered from a robot in their work. They used the 3D data to estimate the depth of segmented objects and built the randomly generated ODMS dataset as a benchmark for their experiments. FasterR-CNN, which is a convolutional neural network that originally used region proposal algorithms to real-time object detection in the MS-COCO dataset. Another piece of related work is FCOS, which stands for Fully Convolutional One-Stage Object Detection. It avoids the high computational cost of anchors in region proposals in favor of fully convolutional one-stage object detection. Also in related work is machine learning and deep learning methods. So one of the papers we considered was Keep Your Eyes on the Lane real-time attention-guided lane detection, which uses ResNet as the backbone for anchor-based feature pooling. This, in combination with an attention-based mechanism and the use of traditional object detection algorithms such as classification and regression, creates a proposal for the position of the lanes. Transformers use encoders, decoders, and self-attention with large-scale datasets in an attempt to replace CNN backbones. More data efficient, they are made more data efficient by the use of augmentation, regularization, as well as distillation of the transformer model with a CNN pre-trained on ImageNet 1000. Another way they further improve these image transformers is through the use of self-supervision and self-distillation. So these are some of the examples of related work in terms of object detection, in terms of using robots to gather image data.
So for our approach, we did two separate things. For both of them, we downloaded the ODMD code and dataset from GitHub using the link shown. And the paper and the code, we used two models, the BoxLS and DBox. The pre-trained DBox model failed to run, but we were able to use the provided code to train the DBox model and run it. So to run the models using the ODMD dataset, we used a Dell Inspiron laptop computer running Windows 10, which used a CPU. So our goal was to regenerate the results found in table 1, which we saw several slides ago. The commands that we used were the demo dataset eval, which made predictions using the pre-trained BoxLS model, the demo dbox train, which we used to train the dbox model, and the demo dbox eval, which we used the trained dbox model to make our predictions. And the results that we obtained were the mean % error for the several scenarios: normalized, object detection with motion, and robot. So the results here are a comparison of the BoxLS, which you see on the left, and the DBox, which you see on the right. And if you take a look at the normal error, you see that there's a 0 error for the BoxLS, but a 0.029 and 0.023 error for the DBox. For everything else, however, DBox performs better by about an order of magnitude compared to BoxLS. So for phase 4, we tried to make improvements to DBox. So as a control, we trained DBox just up to 15,000 epochs, and then we ran it. Note that this is less training time than what we used for DBox in the previous phase, phase 3. For our experiment, we added dropout. We went from the default setting, where the dropout probability was set to 0, to a dropout probability set to 0.1 and 0.3. In each case, we retrained DBox and then we ran it. The results show that DBox did not improve, and in fact, its performance suffered as a result of adding dropout. The error increased for going to dropout equals 0.1, and it increased even further when going to dropout equals 0.3. And as is shown, this was the case for all of the scenarios. So on the left is dropout equals 0.1, and on the right is dropout equals 0.3. So unfortunately, because increasing the dropout only decreased the accuracy of DBox, and increasing dropout from 0.1 to 0.3 decreased accuracy even further. This means that since dropout decreases the amount of data that the model is exposed to during training, our conclusion is that the model was underexposed to data and did not need the regularization provided by dropout. Dropout might improve the model if it is trained for longer, as at that point, the marginal benefit of more training data might be less than the marginal benefit of more regularization. Unfortunately, time constraints prevented us from testing the efficacy of dropout after much longer training times.
These are our references, and that's the end of our presentation. Thank you.